There is something about the night sky that has always made people go quiet. Welcome back to Sleepy Science, where we slow everything down and let the world's most beautiful ideas carry you gently off to sleep. Tonight we're spending time with one of the most quietly extraordinary things our planet has ever produced, the Northern Lights. If you enjoy what we do here, please consider leaving a like, a subscription, and a comment below telling us what topic you'd love to drift off to next. And if you'd like to help keep these videos going, you can always find the Sleepy Science Patreon in the description. Every bit of support means more quiet evenings like this one. Now, let's begin. Somewhere above the Arctic Circle, right now, as you lie still and let your eyes grow heavy, the sky is moving. Not the way it moves when clouds pass across the moon. Not the slow, familiar turning of stars from east to west through the night. This is a different kind of movement. A rippling, a breathing. Curtains of pale green light unfurl across the darkness, like something enormous is sighing. And in a way, something is. The Aurora Borealis, which is the name we give the Northern Lights, is born from something called the solar wind. The sun, that enormous burning thing, so far away you could fit 1,000,000 Earths inside it, does not simply sit still and shine. It exhales. Constantly and in all directions, it sends out a stream of charged particles, electrons and protons, and other tiny things, too small to imagine, streaming outward at speeds of several hundred kilometers per second. You don't feel it. You don't see it. But it is always there, washing past the Earth like a river you will never know you are standing in. This stream, this solar wind, arrives at our planet and meets something it cannot easily pass through. Our planet has a magnetic field, an invisible shell of force generated deep inside the Earth's core, where liquid iron moves in slow and ancient currents. That magnetic field wraps around the world like a cocoon. Scientists call it the magnetosphere, and without it, we would not be here at all. The solar wind would have stripped away our atmosphere billions of years ago, the way it stripped away Mars. But instead, the magnetosphere bends the particles, deflects them, guides them. And where that invisible guidance leads them is toward the poles. Near the North Pole and the South Pole, the magnetic field lines dip down toward the Earth's surface. The charged particles follow those lines, like water following a groove in stone. They spiral downward and plunge into the upper atmosphere, into a layer of air, about 100 kilometers above your head, where the air is so thin, it is barely air at all. And when those particles collide with atoms of oxygen and nitrogen, at those extreme altitudes, energy is released. Light is released. And that light is the aurora. The color of the aurora depends on which atoms are being excited and at what altitude. Oxygen, when struck by those particles, at around 100 kilometers up, glows green. That is the color most people know. The one you see on photographs. The one that ripples across the sky like a living thing. Green, soft and luminous, like light filtered through the thinnest imaginable leaf. But higher up, above 200 kilometers, oxygen produces a different color entirely. Red. A deep, rare, arterial red that blooms sometimes at the very top of the aurora curtains, at the edges where the light is faintest. Not many people see red auroras. They require very active conditions, and they exist at altitudes most of us never look toward. But they are there, high above the green, bleeding quietly into the dark. Nitrogen adds its own palette. At lower altitudes, nitrogen creates blues and purples, deep violet tones at the very bottom of the aurora curtains, where they meet the darker sky. The interplay of these colors, green above and purple below, is the aurora most often painted in photographs. Though the human eye, in darkness, sometimes sees less color than a camera does. The eye adjusts, grows quiet in the dark, and sometimes what a camera captures as vivid green appears to a person standing beneath it as something ghostly white, almost gray, shimmering rather than glowing. That is one of the things that makes the aurora so strange and personal. It looks different depending on the conditions of your eyes, the darkness around you, the sensitivity of your own tired vision. Two people standing side by side beneath the same stretch of sky may describe what they see in entirely different terms. One sees green ribbons. The other sees something barely there, a presence rather than a color, a light they feel more than see. The aurora is not exclusive to the north. The same phenomenon happens at the South Pole, and there it is called the Aurora Australis, the Southern Lights. Both poles produce their auroras simultaneously and almost symmetrically, mirroring each other across the planet, as if the Earth is breathing in two places at once. Satellites have captured images of both auroras, occurring at the same time, glowing rings of light around each pole, the Earth between them, turning slowly in the dark. People have been watching the northern lights for as long as people have looked upward. The oldest written descriptions we have come from ancient Babylonian clay tablets, etched around 500 BC. Astronomers in Babylon, sitting on rooftops in what is now Iraq, recorded strange red glows in the northern sky. They wrote about them carefully, solemnly, because in their understanding, such things were not accidents. They were messages, signs from something larger than themselves. The ancient Greeks had a word for the aurora, or rather, they had a goddess. Aurora was the Roman goddess of the dawn, and the scientist Pierre Gassendi borrowed her name in the 1600s when he tried to give this phenomenon a name that the scientific world might share. He paired it with Boreas, the Greek god of the north wind, Aurora Borealis, the dawn of the north, which is quietly lovely, even before you know what it means. It sounds like something delicate and very old. The Inuit people of the Arctic have lived beneath the aurora for thousands of years. Their traditions hold many stories about it. In some communities, the lights were believed to be the spirits of animals dancing, walrus and seal and fox, moving in the sky above the ice. In others, the lights were the spirits of the dead, playing games with a walrus skull across the vault of night. In still other traditions, the aurora was something to be cautious of, a sign of things coming, a message that required attention and stillness and quiet. There is something worth pausing on here. Across every culture that has ever lived beneath the northern lights, people have instinctively felt that they were witnessing something that mattered. Not just something beautiful, something significant, something that deserved attention. And in a way, they were not wrong. The aurora is significant, not in the way their stories described, perhaps, but in its own quiet, scientific way. It is a visible sign of the sun's invisible breath, the Earth's invisible shield, and the way those two vast forces negotiate with each other across an enormous distance of space. The Norse people called the aurora the Bifrost, the shimmering rainbow bridge between the world of humans and the realm of the gods. When the lights were bright and active, some believed the Valkyries were riding across the sky, collecting the souls of fallen warriors and carrying them to Valhalla. The armor of those great women caught the light of the stars and scattered it back as aurora. There is something about that image that the science does not entirely dispel. The aurora does look like something riding, something sweeping, something on its way somewhere. In Finland, the aurora was called the Revontulet, which translates to fox fires. The myth described a great fox running across the snow-covered fells of Lapland, its tail brushing the sky and sending sparks scattering upward into the stars. The image of that great, quiet animal, running in the dark, its tail leaving trails of light across a frozen sky. There is something about it that feels very right. As if the Finns, over centuries of watching, had somehow captured something true about it. Its wildness, its quickness, its refusal to stay still. The aurora moves constantly. It does not hold a shape. It shifts and folds and retreats and surges. Sometimes it hangs like a curtain across the whole sky, barely trembling, almost peaceful. And then within seconds, it can erupt into something called a corona, where the light appears to radiate outward from a single point directly overhead, like rays from a hidden sun, like a great eye-opening above you. It is startling, even for people who have seen the aurora many times. Even after years of watching, a corona can steal your breath. The movement of the aurora is tied to the movement of the solar wind itself. When that wind is steady and mild, the aurora hangs in gentle arcs, close to the horizon, barely shifting. But when the solar wind intensifies, when a burst of energy leaves the sun and arrives at Earth, the aurora responds. It wakes. It moves to lower latitudes. It brightens. It sometimes becomes visible from places that almost never see it. Scotland, Germany, the northern United States, even rarely as far south as the Mediterranean. These intensifications are called geomagnetic storms. They happen when a particular kind of solar eruption, called a coronal mass ejection, sends 1 billion tons of magnetized plasma hurtling toward the Earth. When that plasma cloud arrives, sometimes a day or two after leaving the Sun, it compresses the Earth's magnetosphere, forces it inward, and triggers aurora activity, far beyond the usual polar zones. The most powerful geomagnetic storm ever recorded struck the Earth in September of 1859. It is known as the Carrington event, named after the British astronomer Richard Carrington, who observed the solar flare that caused it. During the Carrington event, the aurora was seen as far south as Cuba, as far south as Hawaii, as far south as Queensland in Australia. People in the northeastern United States woke up in the middle of the night, thinking it was dawn. The sky was so bright. Gold miners in the Rocky Mountains got up and began preparing breakfast, certain that morning had come. Telegraph operators across Europe and North America found their systems sparking with electricity that had come from nowhere, flowing through the wires, powered by nothing but the aurora above. Some operators, in a kind of bewildered experiment, disconnected their batteries and found they could still send and receive messages, powered entirely by the energy falling from the sky. If an event like that happened today, the consequences would be considerably more disruptive. Modern civilization runs on electrical infrastructure that was not designed to absorb that kind of energy surge. Satellites could be damaged. Power grids could go dark. Communication systems could fail. Scientists who study space weather, and yes, that is a real field of research, take this possibility seriously. They monitor the sun, the way meteorologists monitor the atmosphere, watching for signs of outbursts, for the first hints of something building, 93 million miles away. But the aurora itself, in its ordinary everyday form, is gentle. You would not feel it. You cannot feel the particles passing through the atmosphere above you. You cannot feel the magnetic field lines guiding them downward. The only way you know it is happening is the light. And that light does not produce heat. You can feel on your skin. It does not make a sound. You can hear with ordinary ears. It is simply there, visible and silent and impossibly vast, and then gone. Some people however, claim to have heard the aurora. This has been reported for centuries. A faint crackling, a soft hissing, a swishing sound that seems to accompany intense auroral displays. Scientists were skeptical of this for a long time. The aurora occurs at altitudes far too high for sound to travel to the surface. But in recent years, Finnish researchers set up an array of microphones in an open field on a quiet night and captured sounds that appeared to coincide with auroral activity. The sounds were not coming from above. They were coming from very close to the ground, from the inversion layer, just a few dozen meters up, where temperature differences in the air can create small electrical discharges. The aurora, high above, appears to trigger something subtle and local that can, in very still conditions, in a very quiet place, be heard. Not as a roar, not as anything dramatic. A faint, soft clapping, a sound like someone far away, brushing their hands together gently in the cold night air. The zone around the poles, where auroras appear most often, is called the auroral oval. It is a ring-shaped region, roughly centered on the magnetic poles, rather than the geographic poles, which are not quite the same thing. The magnetic North Pole is the place toward which all compasses point, and it does not sit still. It drifts, slowly, year by year, moved by changes, in the flow of that liquid iron, deep inside the Earth. Over the past 100 years or so, the magnetic North Pole has moved from northern Canada towards Siberia, crossing the Arctic Ocean as it goes. It is currently moving at roughly 50 to 60 kilometers per year, faster than it did in the mid-20th century. Nobody is entirely certain why it has sped up. The auroral oval follows the magnetic pole. As the pole shifts, so does the oval, and so do the places on Earth most likely to see the aurora. At the moment, the best places are roughly between 65 and 72 degrees north latitude. Places like northern Norway, Iceland, northern Finland, Alaska, and the Yukon. These places sit in the sweet spot, neither so close to the pole that the oval passes overhead and moves on too quickly, nor so far south that the oval rarely reaches them. They exist inside the ring of light. To see the aurora, you need several things to come together at once. You need darkness, genuine, proper darkness, which is increasingly rare on this illuminated planet. You need clear skies, no cloud cover to hide the display above. You need solar activity sufficient to produce visible aurora at your latitude. And you need patience. The aurora does not perform on schedule. It does not arrive because you have planned for it. It comes when it comes, sometimes for only a few minutes, sometimes for hours. And sometimes you stand in the cold for a long time, and nothing happens, and the sky stays dark, and you go inside, and an hour later it erupts, in the most magnificent display of the season. This is one of the things veteran aurora watchers will tell you. The aurora teaches you to wait without expectation. It teaches you to stand in the cold and be present without demanding a reward. The people who see the best auroras are usually not the ones who drove to the most calculated spot, with the most sophisticated gear. They are the ones who went out simply to be there, to look upward, to wait. The Aurora Borealis typically sits somewhere between 80 and 300 kilometers above the Earth's surface. The boundary between what we call the atmosphere and what we call outer space is generally set at 100 kilometers, the Kármán line. So parts of the aurora are technically in space. When you look at the aurora, you are looking across the border between the world you live in and the void beyond. There is a rhythm to the aurora that follows the rhythm of the sun. The sun goes through cycles of activity, roughly 11 years long, moving from periods of relative quiet to periods of intense activity, and back again. At the peak of a solar cycle, called solar maximum, sunspot activity is high, solar flares and coronal mass ejections are more frequent, and the aurora is more vivid, more widespread, more reliably seen. At solar minimum, things quiet down. The aurora retreats. The polar nights grow a little darker. We are currently in a period of increasing solar activity, moving towards solar maximum, which makes this a particularly rewarding time to watch the northern sky. People at lower latitudes than usual have been seeing aurora events that would normally be invisible from their locations. The lights have appeared over England, over France, over the Midwestern United States. Briefly, softly, but undeniably there. One of the quieter truths about the aurora is that it is not only visible from the ground. Astronauts on the International Space Station, orbiting the Earth at roughly 400 kilometers up, sometimes find themselves level with the aurora, or even below it. Photographs taken from the station show the aurora as a thin, glowing membrane, a veil of light wrapped around the top of the atmosphere, seen from outside rather than beneath. From space, it looks less like a curtain and more like the edge of something alive, a thin, luminous skin on the surface of the world. The aurora also occurs on other planets. Jupiter has auroras. Saturn has auroras. Uranus and Neptune have them too. Any planet with a magnetic field and an atmosphere can produce this phenomenon. Jupiter's auroras are particularly grand. They appear at its poles and dwarf anything our Earth produces, covering areas larger than our entire planet, burning with energies thousands of times more intense than ours. The Hubble Space Telescope has captured images of Jupiter's aurora that show it as a great glowing ring around the gas giant's poles, permanent and enormous, in a way that makes our own lights seem like something small and precious. Saturn's auroras pulse and shift in ways that differ from Earth's On Earth, the aurora brightens mainly at night, when our side of the planet faces away from the sun. Saturn's auroras, strangely, seem to brighten around dawn at one of its poles, behavior that puzzled scientists when first observed and is still not entirely explained. Even at that enormous distance, the sun still finds ways to surprise us. The color of Jupiter's aurora is different from ours as well. Because Jupiter's atmosphere is made mainly of hydrogen, the aurora there appears largely in ultraviolet light, invisible to human eyes, but captured by instruments as a ghostly blue-white glow. On Earth, our oxygen-rich atmosphere gives us the greens and reds we think of as aurora. Elsewhere in the solar system, the lights would look entirely different to us if we could stand beneath them. Mars, which has almost no global magnetic field, produces a different and more diffuse kind of aurora. Small patches of magnetism exist in Mars's ancient rocky crust, remnants of a time billions of years ago, when Mars may have had a full magnetic field and perhaps a thicker atmosphere. Around those patches, aurora-like glowing has been detected. Brief, localized, like tiny campfires of light, scattered across a cold and airless world. Back on Earth, the science of the aurora did not arrive quickly. For most of human history, the lights were explained through myth and story. Even after the scientific revolution, decades passed before anyone understood what actually caused them. Edmund Halley, the same Halley whose comet still bears his name, proposed in 1716 that the aurora was connected to magnetism. He was onto something, but the precise mechanism, the solar wind, the magnetosphere, the particle interactions, took another 250 years or so to work out fully. Benjamin Franklin, ever curious, suggested in 1778 that the aurora might be caused by electrical charges carried from the equator to the poles by the atmosphere. He was not entirely wrong. Electricity is very much involved, though not quite in the way he imagined. His instinct that aurora and electricity were related was sound, even if the details needed roughly another 2 centuries to be worked out. The Norwegian scientist Christian Birkeland made some of the most important contributions to our understanding of the aurora in the early 1900s. He led expeditions to the far north of Norway to study the lights at close range, not a comfortable undertaking in those decades of sail and cold. He proposed that the aurora was caused by electrons from the sun being guided by the Earth's magnetic field. His colleagues in warmer cities were not convinced. His theory was largely dismissed during his lifetime. He died in 1917, still not fully recognized, and his ideas were not vindicated until the space age, when satellites could directly observe the flow of particles from the sun. Birkeland's portrait appeared on Norwegian currency for many years, 200 krone note his face patient and serious, against a backdrop of the lights he spent his life studying. There is something right about that. The aurora has its own particular feel, in the places that live beneath it regularly. In northern Norway, people have a word, nordlys, which simply means northern light. One word, not a phenomenon, not a spectacle, not an event. Just northern light. The way you might say, the wind, the snow, the dark. Something that is simply part of the world, where you live, familiar without being ordinary. In Iceland, the aurora is woven into the fabric of daily life. In winter, people check aurora forecast apps, the way people elsewhere check rain forecasts. They step outside casually, on a clear night, and glance north before bed. The aurora is not a destination for them. It is not a reason to drive hours into the wilderness. It is the sky above their houses, doing what the sky sometimes does. And yet, even the Icelanders who see it often say it never entirely loses its quality of quietly stopping you in your tracks. There is a scale scientists use to measure geomagnetic activity. It is called the KP index, and it runs from 0 to 9. At KP 0, the field is very quiet, and aurora is only visible from very high latitudes, the edges of the world. At KP 5 or above, conditions are considered active, and the aurora may be seen at considerably lower latitudes. At KP 9, the maximum, something significant is happening. Those are the nights, when aurora chases drive through the night and the lights appear over cities that almost never see them. The KP 9 events are rare. Most nights fall somewhere between 1 and 3, quiet and steady and unremarkable. The aurora on those nights is still happening somewhere above the polar regions, just not strongly enough to spread south where more people might notice. It performs, as it always does, to an audience of a few thousand. Scientists at polar stations, reindeer herders crossing frozen ground, insomniacs staring out of cabin windows in Tromsø or Rovaniemi or Yellowknife. Yellowknife, in Canada's Northwest Territories, is one of the best aurora viewing destinations on the planet. Its position directly under the auroral oval, its generally dry, clear winters, and its small population mean darkness is easy to find. Tour operators there offer aurora packages that include heated cabins with glass ceilings, so that visitors can lie on their backs in warmth and watch the lights move above them without the cold pressing in. To fall asleep beneath the aurora, in a warm bed, with the green and white light shifting silently above, that is an experience people describe with a kind of reverent inadequacy. The words, they say, don't quite get there. The aurora appears for a reason tied to something, called the auroral substorm. A substorm is a brief intensification of activity, lasting from several minutes to a few hours, during which the aurora brightens dramatically and breaks into dynamic movement. Substorms happen when energy stored in the magnetosphere, energy that has been building up, like water behind a dam, suddenly releases. A cascade begins. Magnetic field lines reconnect and snap. Energy flows. Particles plunge. Light erupts. The whole thing might last 20 minutes, and then quiet again, leaving the sky darker than before, and the watcher standing in the cold, wondering if it really happened. During a substorm, the aurora can cover the entire visible sky. Not just the horizon, not just a band in the north, everything. Above you, all the way around you, from horizon to horizon, the sky on fire with silent light. Green and white, and sometimes purple at the lower edges, sometimes crimson at the top, rays and curtains and coiling forms that move faster than you can follow and slower than you can believe. People who have witnessed this sometimes describe it as feeling very small. Not frightened, not overwhelmed in a bad way, simply made small in the most peaceful sense, as though the usual sense of being the center of your own story quietly dissolves, and what is left is just a person standing in the dark, watching something far older and larger than anything human move across the sky. The aurora has been captured in art for as long as humans have made art. In Norway and Greenland, ancient rock carvings have been interpreted by some researchers as possible depictions of aurora. The interpretation is debated. It is hard to know, across thousands of years of distance, what a carving meant to the hand that made it. But the possibility is there. The possibility that someone, long before cities or writing, stood beneath the lights and felt the urge to make something, to scratch into stone what the sky was doing, so it could be remembered. The Norwegian artist Edvard Munch painted the aurora more than once. His version is strange and moody, as you would expect. The lights in Munch's paintings pulse with something anxious, the same restless energy that animates his other work. The German Romantic painter Caspar David Friedrich depicted polar scenes and cold skies in ways that carried aurora-like qualities, even when the aurora itself wasn't explicitly present. The sense of a vast cold above, pressing down on a small human figure. Frederick Edwin Church, the American landscape painter, created a large and luminous aurora painting in 1865 that is considered one of the finest depictions of the phenomenon in Western art. He traveled to Labrador to observe icebergs for his work and his aurora study, all cold blues and greens and pale fire, captures something of the eerie calm of seeing the lights over ice and open water. The aurora also appears in literature, inevitably. Philip Pullman used it as a doorway between worlds in his Dark Materials trilogy. The lights in his books are portals, thin places where the fabric between parallel universes grows almost transparent. It is a beautiful metaphor, and not entirely wrong in the way it feels, because there really is something at the aurora that feels like a membrane, an edge, a place where one kind of world meets another. The aurora has a relationship with the seasons. Because you need darkness to see it, the aurora is effectively invisible during the Arctic summer, when the sun does not fully set, for weeks or months at a time. The midnight sun and the aurora cannot share the same sky. One belongs to endless, pale daylight. The other belongs to the long dark. So the aurora season runs roughly from late August to early April, the months when night returns to the north. There is something bittersweet about this. The Arctic summer is luminous and alive, the sun barely dipping below the horizon. And then gradually, day by day, the dark creeps back. The nights grow longer, and with the dark, the aurora returns. The people who live in those places say that the return of the aurora is one of the consolations of the returning winter, that the darkness brings its own light, if you know to look for it. Around the equinoxes, March and September, aurora activity tends to peak. This is partly because of the geometry of how the Earth's magnetic field aligns with the solar wind around those times. At the equinoxes, the orientation is more favorable for the solar wind particles to enter the magnetosphere. More gets in. The aurora brightens. Spring and autumn, then, are the best seasons to chase aurora. Dark enough to see it, but not yet the depths of polar winter, with its brutal, cold, and inaccessible roads. The International Space Station passes over the auroral zones on many of its orbits. Astronauts have reported seeing the lights below them, looking down rather than up, watching the glowing oval revolve slowly beneath the station as the Earth turns. Scott Kelly, who spent nearly a year aboard the station, described the aurora as one of the most arresting things he had ever seen from space. He had seen typhoons, volcanoes, ocean storms, and the aurora, he said, was among the most quietly extraordinary. The aurora has a counterpart in a phenomenon called STEVE, Strong Thermal Emission Velocity Enhancement. This acronym was invented somewhat playfully by a group of citizen scientists who had been photographing unusual purple and green streaks in the sky that did not match typical aurora. STEVE appears as a narrow ribbon of mauve or purple light, usually east-west in orientation, and can be seen at lower latitudes than normal aurora. For years, it was assumed to be aurora, but researchers eventually determined that it has a different mechanism. It appears to be caused by fast-moving streams of hot gas in the upper atmosphere, rather than by particle precipitation. STEVE is still not fully understood. It is, in a sense, a new phenomenon, something that was there all along, photographed many times, simply not yet explained. This is one of the more quietly remarkable things about aurora science. We have been watching the northern lights for thousands of years. We have sophisticated instruments in orbit. We have ground-based cameras watching every clear night. And still, new things appear. New phenomena with new mechanisms, new behaviors that do not quite fit any existing model. The sky above the poles is still, in some sense, a place of ongoing discovery. The study of the aurora has led to a broader understanding of plasma physics, the science of ionized gases, which make up the vast majority of visible matter in the universe. Stars are plasma. The solar wind is plasma. The aurora is what happens when plasma from our star meets the edge of our world. Understanding how plasma behaves in a magnetic field, how particles follow field lines, how energy transfers and dissipates. All of this flows from aurora research. The lights above the poles, in other words, are a laboratory as well as a spectacle. Nuclear fusion research, the attempt to replicate inside a machine the process that powers the sun, draws on plasma physics, refined in part through understanding the aurora. The same principles that describe how particles flow along magnetic field lines in space apply to how particles behave in a fusion reactor. The aurora is not only beautiful, it is practically connected to the future of energy. Auroras also interact with satellites in ways that engineers must account for. During intense geomagnetic storms, satellites in low Earth orbit can be subjected to increased drag as the upper atmosphere expands slightly due to the additional energy input from the aurora. The atmosphere breathes outward just a little, and satellites moving through it slow down, lose altitude, require adjustment. In February of 2022, a geomagnetic storm struck shortly after. A large batch of Starlink satellites were launched. The increased atmospheric drag prevented most of them from reaching their operational orbits, and nearly 40 were lost. The aurora, at that moment, reached up from below and quietly swallowed a small constellation. The altitude of the aurora varies with the type and energy of the particles involved. Low-energy electrons may only penetrate to around 300 kilometers, producing the high red aurora. Higher energy electrons go deeper, reaching 100 kilometers or below, producing the bright green. And the most energetic particles of all can reach even lower, producing rare and patchy blue aurora at the very base of the display. The aurora is, in a sense, color-coded by energy. The higher the light, the lower the energy that made it. The structure of the aurora is not random. The curtain shapes, the rays, the arcs, these all reflect the structure of the magnetic field lines along which the particles travel. The aurora is, In a real sense, a map. A glowing map of invisible forces, drawn in the sky by particles following invisible roads. If you knew how to read it, the aurora would tell you about the shape of the magnetosphere above, about where the field lines converge, about what the sun has been doing. Scientists do read it, in a sense. Networks of cameras across the Arctic image the aurora continuously, tracking its movements, analyzing its shapes, mapping its magnetic context. These all-sky cameras, fisheye lenses pointing straight upward, capture the full auroral oval and transmit their images to scientists who use them to understand what is happening in the space above. Some of these camera networks stream live to the internet, and on active nights, you can watch the aurora over Norway or Iceland or Alaska, from wherever you are in the world. The aurora produces its own radio emissions. When electrons spiral along magnetic field lines, they emit radiation across a range of frequencies, including radio waves. These radio emissions, called auroral kilometric radiation, are generated at altitudes above the aurora itself and propagate outward into space. They are strong enough that Jupiter's aurora, far across the solar system, was first detected not by light, but by radio. Astronomers noticed unusual radio bursts from Jupiter's direction in the 1950s and eventually traced them to the giant planet's intense auroral activity. There is something strange and beautiful in the idea that the aurora sings, in a way, that it broadcasts, that if you had the right kind of ears, you could hear it across the solar system, this faint crackle and hiss of light made from magnetism and streaming sunlight, and the thin screaming electrons of a distant star's breath. The word aurora itself has a gentle etymology. In Latin, aurora means dawn. The Romans imagined a goddess who rode across the sky each morning in a chariot drawn by horses, spreading rosy light before her as she cleared the way for the sun. There is a poetic alignment between that image and the actual aurora, which does appear often in the hours before and after midnight, which does ripple across the sky like something in motion, which does carry a quality of beginning, of opening, of light arriving from somewhere you cannot quite see. The most intense part of the auroral oval is called the auroral zone, and places within it can experience auroral activity on roughly 200 or more nights per year. 200 nights. More than half the year, the sky above those places is doing something remarkable. Most of those nights, clouds intervene. Weather complicates everything. But on the clear nights, and in the Arctic winter, there are many clear nights. The lights are simply there. Available. Ongoing. Part of what the sky does in the long dark. In some Arctic communities, children grow up with the lights as a backdrop to winter nights. School lets out in the dark, They walk home under green or white sky shimmer. It is not special for them, in the way it might be special for someone who has traveled a long distance to see it. But they carry it with them. When they move south for university or work, they find they miss it. They find they look north on clear nights, out of habit, looking for something that is no longer there, from where they now stand. The aurora has been connected historically to superstition and omen. In parts of Scotland and Scandinavia, a particularly bright red aurora, which occurs much less often than the green, was sometimes interpreted as a sign of war or disaster. The red lights in the north, glowing like distant fire, would indeed be unsettling if you did not know what caused them. The Carrington event of 1859, before being understood scientifically, caused widespread alarm among people who saw a blood-red sky pulsing over their farms and fields. There were genuine reports of panic. People who had never seen the aurora at all, living in latitudes where it was essentially unknown, woke to find the sky on fire with light. Some believed it to be a great conflagration somewhere. Some knelt in their fields and prayed. Some sent frantic messages to distant relatives, asking if they were safe. The fact that the telegraph operators, even as they received those messages, were experiencing their own electrical chaos from the same storm was not reassuring. The aurora carries a quality of scale that other natural phenomena rarely achieve. A storm cloud is large. A mountain range is large, but the aurora is planetary. The auroral oval is roughly the size of a continent. The curtains and arcs you see above you extend thousands of kilometers across the top of the world. When you look at a single ribbon of green light, stretching from horizon to horizon, you are looking at something hundreds or thousands of kilometers long. And yet it moves. And yet it changes. And yet it is made of something, too small to see individually, particles smaller than atoms, each contributing its tiny quantum of light to the whole. Tens of billions of electrons are falling through the upper atmosphere at any given moment during an aurora. 10 billion individual particles, each one following its magnetic thread, each one releasing a tiny flash of energy when it strikes an oxygen or nitrogen atom. Together, those flashes merge into the curtain of light that you see when you tilt your head back. In the cold night, the scale going downward, subatomic to quantum, to atomic, to molecular, is as staggering as the scale going upward, from atmosphere to magnetosphere to solar wind to the sun itself. The aurora is a meeting, a negotiation between scales. In folklore from Greenland, particularly among some Inuit groups, there was a practice of whistling at the aurora. Whistling was said to invite the lights to come closer, to draw them down. The response required whistling back, or sometimes snapping fingers, or waving a handkerchief in the cold air. There are accounts of people lying on the snow, whistling softly up at the green sky, and feeling genuinely, that something was listening. Whether or not you believe anything was, there is something touching about it, about the impulse to communicate with the vast and beautiful thing above. The same impulse lives in the aurora photographs people take now. The need to capture it, the need to say, "I was there. I saw this. This happened." Aurora photography has become its own art form, with practitioners spending nights in extreme cold to find the right foreground. A frozen lake, a snow-covered mountain, a lone tree silhouetted against green light, and the right moment when the light does something that the camera can catch. The best aurora photographs have a quality of unreality, a feeling that what you're looking at cannot quite be this world. Long-exposure photography reveals things about the aurora that the naked eye misses. Colors are deeper, structures are sharper. The subtle pink and magenta tones that are almost invisible to the eye appear in photographs as vivid bands. The camera is more sensitive than the dark-adapted eye, more patient, capable of accumulating light over 30 seconds or a minute, in ways the eye cannot. And so, aurora photographs are in some sense more than what any single person sees. They are a composite of time, a gathering together of many seconds of light into one still image. There is a phenomenon connected to the aurora called the pulsating aurora. This is a type of aurora that appears as diffuse, irregular patches of light that brighten and dim rhythmically, like something breathing. The patches pulse with periods of a few seconds to a few tens of seconds, brightening, fading, brightening again. Pulsating aurora tends to appear late in the night, after a substorm has ended, as if the sky is settling down. After excitement, breathing in and out. The mechanism of pulsating aurora involves waves in the magnetosphere, called chorus waves, which are electromagnetic waves at audio frequencies that sound, when played through a speaker, remarkably like bird song. Scientists who first converted these radio waves into sound described them as a chorus of birds, calling at dawn, hence the name. These chorus waves interact with electrons in the magnetosphere, causing them to precipitate into the atmosphere in rhythmic pulses, and those pulses produce the breathing, pulsing aurora. The sky singing to itself, in frequencies no unaided ear can hear, and the song producing light. The relationship between the aurora and Earth's atmosphere is not purely visual. During intense auroral activity, the upper atmosphere is actually heated. The energy deposited by the precipitating particles warms the thermosphere, the layer of atmosphere where aurora forms, by hundreds of degrees. This heating drives atmospheric circulation, causes the atmosphere to expand, and can affect weather at lower altitudes, though the connections are complex and still being studied. The idea that a geomagnetic storm far above might, in some small, measurable way, influence the weather at the surface below, that the sky connects all the way down in this invisible conversation, is one of the more quietly remarkable threads in atmospheric science. The colors of the aurora at the very edge of space, at altitudes of 500 to 1,000 kilometers, are almost never seen. At those heights, the atmosphere is so thin that only the most energetic events produce visible light. But instruments have detected auroral emissions, reaching all the way to those heights, extending the range of the phenomenon, far beyond what the eye could ever follow. The aurora is taller than you think. It reaches higher. It extends into space, further than any photograph could show. There are auroras we cannot see at all. X-ray auroras, ultraviolet auroras, infrared auroras. These occur at the poles, invisibly, simultaneously with the visible lights, detected only by instruments designed to receive those wavelengths. The full spectrum of the aurora is therefore invisible to us. What we see, the green curtains, the red fringes, the purple lower borders, is only a small slice of everything that is happening. The visible aurora is a keyhole view into something much larger. The length of an aurora display varies enormously. A brief substorm might last 20 minutes. A large geomagnetic storm might sustain visible aurora for 6, 8, 12 hours. During the Great Storm of 2003, called the Halloween Storms, the aurora was visible over much of Europe and North America for multiple nights in a row. Power grids in Sweden were disrupted. Satellites experienced problems, and millions of people who had never seen the aurora before looked up from their cities and saw something moving in the sky that they could not quite explain. The aurora has been detected beyond our solar system. In 2015, astronomers detected aurora-like radio emissions from a brown dwarf, a failed star, too small to sustain nuclear fusion, sitting alone in space, without a sun to orbit. This aurora was millions of times more powerful than anything on Jupiter. It lit up the brown dwarf's atmosphere with extraordinary energy caused by interactions between the dwarf's own magnetic field and the plasma of its environment. The aurora, it turns out, is not a peculiarity of our solar system. It is something the universe does, wherever the conditions are right. There is a technology called the Aurora Early Warning System, operated by agencies including NOAA and the European Space Agency. Satellites sit between the Earth and Sun, about 1.5 million kilometers from Earth, at a gravitational balance point called the Lone Lagrange point. From there, they watch the solar wind before it reaches us, measuring its speed, density, and magnetic orientation. When something significant is heading our way, these satellites give roughly 15 to 60 minutes of warning. Not long, but enough. Enough for power grid operators to prepare. Enough for aurora chasers to look north. The Kármán line, the boundary between atmosphere and space, is named after Theodor von Kármán, a Hungarian-American engineer and physicist. He calculated where Earth's atmosphere becomes too thin for aerodynamic flight, where wings generate no useful lift. That boundary, at roughly 100 kilometers, is where the aurora often begins. Space, in that sense, starts right where the aurora starts. The lights are the handshake between our world and everything beyond it. In recent years, citizen science has transformed aurora research. Apps like Space Weather Live and Aurora Notify allow millions of people worldwide to receive alerts when geomagnetic activity rises. And those same people, prompted by their phones, go outside, look up, and if they see something, report it. Photographs are shared. Locations are noted. Together, the reports build a picture of how far the aurora has spread. On any given night, a picture no single observing station could ever build alone. This is how Steve was formally documented. Citizen scientists photographing unusual lights that didn't match standard aurora descriptions, sharing those photographs online, drawing the attention of researchers who then studied the data. The phenomenon had existed, presumably, for as long as the magnetic field had, but it took thousands of amateur observers with smartphones and enthusiasm to bring it to scientific attention. The aurora has a different character. In different places, even within the auroral zone. The lights, seen from the coast of northern Norway, over a black winter sea, have a different quality than those seen from the interior of Alaska, above a spruce forest. The lights seen from sea ice in Svalbard, where no trees and no people are visible, only snow and distant mountains and stars, have a quality of absolute solitude. The setting shapes what the light does to you. The same aurora can feel intimate above trees and vast beyond imagining above open ice. Svalbard is an archipelago in the high Arctic, roughly halfway between Norway and the North Pole. In winter, it enters polar night, a period when the sun does not rise at all. This darkness lasts roughly 4 months. During that long dark, the aurora is the dominant feature of the sky on clear nights. The people who choose to live in Svalbard through that dark, several thousand of them in the main settlement of Longyearbyen, develop a relationship with the lights that is hard to convey in words. The lights become a kind of companionship, a sign that the sky is still active, still alive, even in the deepest dark. The temperature required to produce the aurora's colors in the upper atmosphere is extraordinary. The thermosphere, where most aurora forms, has temperatures that can reach 2000 degrees Celsius or more, but it would not feel hot to you. The air there is so thin, so vanishingly few molecules per cubic centimeter, that the heat cannot transfer. Temperature in the usual sense, is a measure of how fast molecules are moving. In the thermosphere, the molecules move very fast, but there are almost none of them. It is the difference between a hot oven and a single, very fast spark. The spark is energetic, but it cannot warm you. The Aurora Borealis and Aurora Australis are not always perfectly symmetric. The ideal picture is of two matching ovals, one at each pole, mirror images of each other. But the magnetic field is not perfectly symmetrical, and the solar wind arrives at an angle, and the geometry is never ideal. The two auroras can differ in brightness, in extent, in structure. They influence each other across the planet's diameter in ways we are still exploring. The connection between them runs along the magnetic field lines that link the two poles through the interior of the Earth. Conjugate observations, simultaneous observations from both poles, have revealed moments when the two auroras exhibit surprisingly similar structures at the same time, the same shape, glowing at opposite ends of the world, produced by the same stream of particles, splitting and diving into both hemispheres. There is something worth sitting with in that image. The same light, the same moment, above the Arctic, and above Antarctica, the Earth between them, dark and unaware. When the magnetic poles flip, and they do flip, though rarely on human timescales, the aurora would shift too. The Earth's magnetic poles have reversed hundreds of times over the planet's history. The last reversal was roughly 780,000 years ago. During a reversal, which takes thousands of years rather than a sudden flip, the magnetic field weakens considerably. During the transition, auroras could appear at lower latitudes than usual, the auroral zone spreading toward the equator. People in the tropics might see the lights. People everywhere might look up one night and find their sky doing something it had never done before. There are signs that the magnetic field may be changing, weakening in some areas. The South Atlantic anomaly, an area of weak magnetic field off the coast of South America, has been growing and shifting. Satellites passing through it experience more particle bombardment than usual. The anomaly is sometimes called the Bermuda Triangle of space. Whether it is an early sign of a coming reversal or simply a local fluctuation is not yet known. These things move on timescales that make human patience look very small indeed. The aurora can be forecast to a degree. Just as meteorologists use pressure systems and satellite data to predict tomorrow's weather, space weather forecasters use solar observations to predict upcoming geomagnetic activity. When a large coronal mass ejection is detected leaving the Sun, forecasters calculate its likely speed, direction, and magnetic orientation. If those factors suggest it will interact with Earth's field, alerts go out. The aurora community prepares. Cameras are pointed north. Drives are made into the countryside. People stand in fields at midnight, waiting for a storm born on the sun 3 days ago to arrive. The social experience of aurora watching has its own quiet culture. Small groups gather at dark sky sites, cameras on tripods, breath misting in the cold. There is usually not much talking. People stand apart from each other, each one looking upward individually, together in the darkness, but each alone with the sky. When the aurora brightens suddenly, someone sometimes makes a sound, not words, something more involuntary than words. A soft intake of breath, a single syllable that means, yes, there it is. The Northern Lights have a particular quality in relation to other natural spectacles. A great waterfall is loud. A volcanic eruption is violent. A thunderstorm is threatening. The aurora is none of these things. It is very large and completely silent and entirely without menace. It does not ask anything of you. It does not require a response. You can stand beneath it and be entirely passive, just a small creature in the cold, watching something happen that has nothing to do with you, and yet encompasses you completely. There is a particular experience that some aurora watchers describe as the lights coming overhead. When the aurora is directly above you, a corona, the rays radiating from a single zenith point, the usual visual anchors disappear. There is no horizon in your field of view. There is only upward and light and movement. People sometimes lose their sense of which way is down. The usual vestibular confidence wavers slightly, as if the sky is so large and close that the body becomes uncertain. Which way gravity runs. It is a momentary dissolution, very gentle, very strange, and then the light shifts. The corona dissolves, and the horizon returns, and you are standing on solid ground again, blinking slightly, more present in your body than you were a moment before. The aurora is sensitive to very local geography. Mountains affect airflow in ways that affect cloud cover, and cloud cover determines whether you see the aurora. Coastal regions have more moisture in the air, more cloud probability, more chance of being rained out on a night you had planned to watch. Inland continental areas like Fairbanks, Alaska, or Yellowknife in Canada have drier, clearer skies more reliably. Even within a small region, driving to a valley that has a different microclimate from the coast can mean the difference between a night of cloud and a night of green sky. The most photographed aurora locations in the world tend to cluster around a few features. Frozen lakes that mirror the lights above, offering perfect reflections. Birch forests white with snow, their pale trunks glowing faintly green. Dramatic coastlines where dark water meets the sky. The Lofoten Islands of Norway are particularly prized by aurora photographers. Dramatic peaks rising from the sea, small wooden fishing cabins on the water, and above it all, on a good night, the green flowing overhead. Iceland offers the additional drama of volcanic landscapes beneath the aurora, lava fields, and geothermal pools, and glaciers, all illuminated from above by something ancient and cosmic. Bathing in a warm geothermal pool while the aurora moves overhead is one of those experiences that people describe as impossible to adequately communicate. Warm below, light above, cold air on your face, the sky doing something you could watch until it simply stops. The aurora plays with the perception of time. People standing beneath an intense display often report that time behaves oddly, that what felt like 15 minutes turns out to have been 2 hours. The usual sense of time passing, which is tied to a series of small events and thoughts, gets suspended somehow. The display occupies the attention so completely, so fully, without demanding anything back, that the internal clock simply lets go. This is not unique to the aurora. It can happen with any deeply absorbing, beautiful thing. But aurora watchers mention it consistently. The night passes. They did not notice. They were elsewhere. There is a subset of aurora science, devoted entirely to the sounds of the magnetosphere. The chorus waves mentioned earlier are just one of many plasma waves that propagate through the region between the Earth and the solar wind. There are also hiss emissions and whistler waves produced by lightning strikes on Earth that travel upward through the ionosphere and propagate along field lines into the magnetosphere. When converted to sound, whistler waves make a distinctive descending tone, a wheeoop falling in pitch, like a cartoon sound effect, that is somehow also completely natural. The magnetosphere is noisy in electromagnetic terms. It hums and whistles and sings in frequencies that no ear could detect directly, but which, played through the right instruments, form a strange and continuous music. Some artists have taken this seriously. Composers and sound designers have taken recordings of magnetospheric waves, chorus waves, hiss, whistlers, ion cyclotron waves, and composed music with them. The music sounds alien and organic at once, like something at the edge of familiarity, recognizable as sound, but not quite like anything human-made. The aurora has a relationship with time, in another sense as well. In the geological record, there are chemical signatures in ancient ice cores and sediment layers that indicate past periods of intense solar activity and corresponding intense aurora. Scientists can look back in time through these records and piece together the history of the sun's behavior over thousands of years. Periods of unusual quiet, the Maunder minimum of the 17th century, for example, when sunspots nearly disappeared for decades, correspond to periods of reduced aurora reports. In historical records, the Maunder minimum coincided roughly with the coldest part of the Little Ice Age, a period of cooler global temperatures that lasted from around 1300 to around 1850. The connection between solar activity, aurora, and climate is complex and not fully established, but it suggests that the sun's variability and its interaction with our atmosphere has consequences that reach all the way to the surface of the world. There is a concept in aurora science called the magnetospheric tail, or magnetotail. The Earth's magnetic field, shaped by the constant pressure of the solar wind, is not a perfect sphere. On the sunward side, the solar wind compresses it, pushing it inward. On the night side, the field stretches out behind the Earth, like the tail of a comet, extending millions of kilometers downwind of the sun. This magnetotail is where much of the energy builds up before a substorm. When that energy is released, it snaps back toward the Earth, the field lines reconnecting, the aurora flaring. The magnetotail is, in a sense, a coil, a spring under tension, loading and releasing in the rhythm of the solar wind. Each release produces a substorm. Each substorm produces aurora. The system is not random. It has a structure, a repeating mechanical logic that plays out in the sky above the poles, night after night after night. The Aurora Borealis has inspired more poetry per square kilometer of its occurrence than almost any other natural phenomenon. Poets from Lapland and Iceland and medieval Scandinavia wrote about the lights as though they were speaking of something sacred. Contemporary poets continue to return to them. There is something about the aurora that refuses to be described in prose. It demands metaphor. It demands something oblique, something that approaches it sideways, rather than head-on. Perhaps because the thing itself resists being looked at directly for too long. Not because it's too bright. The aurora is rarely that, but because it is always changing. Look at one part of the display, and it shifts somewhere else. Try to follow the movement, and it becomes something else entirely. The only way to experience the aurora is to let go of the impulse to track and capture, and simply look at the whole of the sky at once. Open your gaze wide. Stop focusing. Let it come. That particular mode of looking, wide and soft and unfocused, is also, not coincidentally, very close to the state of mind that precedes sleep. The moon affects the aurora experience. A full moon can illuminate the landscape beautifully, making the foreground of an aurora scene ghostly and blue-white. But a full moon also brightens the sky enough to reduce the visibility of fainter aurora. The ideal conditions for aurora watching are a new moon, clear sky, active geomagnetic conditions, and a location well away from city light. All four things need to align. This rarity is part of why a good aurora sighting feels like a gift. In some traditional Inuit beliefs, the aurora held a particular danger. Children were warned not to whistle at the lights. or they might descend and sweep the child away. This belief about danger may have served a practical purpose, keeping children indoors on very cold nights when the aurora was active. But it also reflects something true about the emotional texture of the lights, their scale, their power, the way they can make you feel small in a way that is exciting to an adult and perhaps frightening to a child. The aurora does not happen every night, even in the auroral zone. Nights when nothing happens are more common than nights when the lights appear, and when they do appear, they may last only minutes, or they may be present all night. This unpredictability is part of the nature of the thing. It comes on its own terms. The solar wind does not consult your schedule. The magnetotail does not check your calendar. The substorm fires when the physics says it should fire, and not a moment before. There is a discipline in aurora watching that has nothing to do with equipment or knowledge. It is the discipline of simply showing up, going outside, looking, accepting that the sky may give you nothing tonight, and going out again tomorrow. Aurora photographers talk about this with a kind of calm resignation. The good nights make up for the empty ones, and the empty ones teach you how to wait without resentment. The very first photograph of the aurora was taken in 1838 by a German daguerreotypist named Johann von Meidler. Or so it is sometimes claimed. The historical record is uncertain. The first definitively documented aurora photograph was taken in 1860 by Thomas Ranger in Norway. Even then, the exposure times required were very long, and the resulting images were smeared and indistinct. It took decades of photographic development before the aurora could be reliably captured with any detail. And now, with modern digital cameras capable of extraordinary low-light sensitivity, photographers routinely capture colors and structures that earlier generations could barely imagine. The aurora was first formally named in 1621 by the French philosopher Pierre Gassendi. He observed a particularly dramatic display over southern France, unusual for that latitude, and applied the term Aurora Borealis in the first written use of that phrase. Galileo Galilei also saw the same display and wrote about it, incorrectly concluding that sunlight reflecting off the edge of the atmosphere caused the glow. Even Galileo got it wrong. The phenomenon was genuinely mysterious, and the right answer: solar wind particles, guided by magnetic fields, was simply not yet within the reach of available science. The aurora provides a visible demonstration of Earth's magnetic field lines. The bands and rays and curtains are not arbitrary shapes. They trace the invisible structure of the field. The field lines converge at the poles, and so the aurora concentrates there. Where the field lines are closely spaced, the aurora is brighter. Where they are more diffuse, the aurora is softer and more spread out. Reading the aurora is, in a way, reading the magnetic body of the Earth, its invisible self, made briefly visible in light. deep inside the Earth. At the very center, liquid iron flows in patterns, driven by heat escaping from the inner core. This flow is what generates the magnetic field through a process called the geodynamo. The geodynamo has been running continuously for at least 3.5 billion years, almost as long as the Earth has been solid enough to have a core. Without it, we would not have a magnetosphere. Without the magnetosphere, we would not have the aurora. But more importantly, without the magnetosphere, we likely would not have an atmosphere at all. The aurora, beautiful as it is a side effect of what keeps us alive. The Maori of New Zealand have a term for the Aurora Australis, Tahuna Nui Arangi, or the Great Bonfire of the Heavens. The Southern Lights, seen from the South Island of New Zealand on active nights, carry the same quality of unearthly beauty as their northern counterpart. The experience of watching them from Rakiura Stewart Island, the southernmost inhabited part of New Zealand, over a dark southern sea, is something that has drawn travelers from the other side of the world. Antarctica, below the southern auroral oval, offers perhaps the most extreme aurora viewing on the planet. The Antarctic research stations, Scott Base, McMurdo, Concordia, experience months of polar night. The scientists and support staff who winter over at these stations live beneath the southern lights for months of continuous dark. The psychological effect of polar night is real and studied. The extended darkness can be difficult, but the aurora is reliably described as one of the most sustaining features of the long winter. People who have wintered at polar stations sometimes say that the aurora becomes almost personalized over time. You know its rhythms. You know what kind of night is likely to produce a display. You develop preferences. The quiet, diffuse arcs of a mild night versus the wild dancing of a substorm. You come to recognize patterns, the way you recognize weather patterns from long experience with a particular climate. The sky becomes familiar. Not ordinary, but familiar. There is a tradition in some parts of Scandinavia of watching the aurora for its shape and attempting to read something from it. Not in a formal prophetic sense, but in the way that people read clouds. This shape like a fish, that formation like a wave. The aurora's constant motion and transformation invites this kind of reading. It is almost narrative in quality. It has a beginning and a development, and a fading, something that moves through a story arc, over the course of an hour or a night. The aurora has no favorite time of night, but there is a tendency for substorms to occur more often, in the hours around local midnight. This is connected to the geometry of the magnetotail. When a particular region of the auroral zone rotates into the anti-sunward position, it aligns with the part of the magnetotail where energy tends to release. Midnight is therefore often the best time to watch, which means the aurora rewards the people who stay up late, who resist the warmth of bed, who push through the fatigue and go outside one more time. Though sometimes, in the very early hours of the morning, a particularly quiet and beautiful aurora appears. Soft arcs hanging in the north, barely moving, the sky gradually brightening around them as dawn approaches, and the arc slowly fades into the coming day. The aurora yielding to the sun, the night giving way, the very last sight of something ancient, before the daylight takes everything back. Some people have tried to live entirely within the aurora's seasonal rhythms, spending months in Lapland or Alaska, building lives around the possibility of aurora. There are tour guides in Tromsø who have led aurora expeditions every winter for decades, who have probably seen the lights 10,000 times or more, and who still stop talking. When a display appears, still look up for a moment before continuing with whatever they were doing. That capacity for renewal, to be still moved by something seen thousands of times, is perhaps the most quietly extraordinary thing about the aurora, and perhaps about any truly beautiful thing. The aurora produces its own heat, in a sense. Not warmth you can feel, but the particle bombardment of the upper atmosphere deposits energy there. That energy heats the thermosphere. The heated thermosphere expands. The expansion affects satellite orbits. The aurora, then, has physical consequences beyond its own light, rippling downward through atmospheric layers, affecting the space around the planet, leaving traces in the ionosphere that persist for hours after the display has ended. The ionosphere, a layer of the upper atmosphere where atoms are ionized by solar radiation, is the layer through which radio waves travel. Before satellites, long-distance radio communication depended on reflecting signals off the ionosphere. Geomagnetic storms, which disturb the ionosphere significantly, could disrupt radio communications globally. Ships at sea, aircraft, military communications, all of these could be affected by what was happening in the polar sky. The aurora was not merely beautiful. It was, sometimes, a strategic problem. During the Second World War, geomagnetic activity was tracked partly for its effects on military radio communications. Periods of high aurora activity could degrade the ability of troops to coordinate, ships to navigate, bombers to receive instructions. The sun's activity, manifested in the polar skies as light, had consequences measured in military operations, thousands of kilometers from any aurora. The Global Positioning System, GPS, can also be degraded during intense aurora activity. The charged particles disturb the ionosphere in ways that affect the propagation of the radio signals used by GPS satellites. Accuracy decreases. Positions shift. For most everyday users, this matters very little. For precision agricultural equipment, for surveyors, for air traffic control, for maritime navigation in tight channels, it can matter considerably more. Space weather agencies monitor GPS degradation during geomagnetic events as carefully as they monitor anything else. There is something almost impossible to convey about what it is like to be beneath the aurora for the first time. Many people describe a feeling of being somehow both very small and strangely at peace. The size of the phenomenon should perhaps be frightening. The thought of what it represents, the sun's energy, the planet's magnetism, the cold of space just above, should perhaps be unsettling. But almost no one describes it that way. Almost everyone describes it as beautiful, in a way that quiets them down. That turns the usual internal noise down, 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 until there is just the cold and the dark, and the light above. Let's let the science rest for a moment, and simply be with that image. You, somewhere cold and dark. Above you, a river of pale green light, moving across the sky, with the slow urgency of something enormous. No sound, no warmth from the light, just the color and the motion and the cold stars behind it, and the understanding, held loosely, that what you are seeing is the sun's breath finding the edge of the world and glowing. The aurora's scientific study continues to yield new findings. In 2019, researchers published observations of a previously undocumented structure in the aurora. Narrow, fast-moving stripes of diffuse aurora, running east-west, appearing in sub-second bursts, moving through the night sky at several kilometers per second. These structures, informally called the dunes, turned out to be caused by atmospheric gravity waves, large-scale ripples in the atmosphere, moving through the mesosphere and lower thermosphere. The aurora, illuminating those ripples, made the invisible structure of the atmosphere temporarily visible. The aurora as instrument, a way of seeing things otherwise invisible. This is one of the recurring themes in aurora science. The aurora as revealer. It reveals the magnetic field. It reveals the solar wind. It reveals the structure of the upper atmosphere. It reveals the extent of geomagnetic disturbance. Every aurora event is a performance, yes, but also a data set, a transmission, an involuntary self-portrait of the space environment around our planet. There is an aurora alert network that uses smartphones in a novel way. Researchers discovered that the magnetometers built into smartphones, the sensors that allow your phone to act as a compass, can detect changes in the local magnetic field caused by geomagnetic storms. Millions of phones simultaneously recording magnetic field data could, in theory, form a global network of ground-based magnetometers tracking geomagnetic disturbances with a spatial resolution no fixed instrument network could achieve. Your sleeping phone on the bedside table, sensing the aurora above. The aurora is, in the end, a consequence of where we are, orbiting a reasonably active star, protected by a magnetic field, wrapped in an atmosphere. These three things, the star, the field, the air, interact to produce the light. Change any one of them significantly, and the aurora disappears. Too quiet a star, and there is not enough solar wind, no magnetic field, and the particles hit everywhere, not just the poles. No atmosphere, and there are no atoms to excite. The aurora exists because of a particular, improbable, beautiful alignment of conditions. We are fortunate, in a quiet way, to live on a planet where this can happen, where looking up on a clear winter night from the right place on Earth can produce something like this. Something that has no survival value, no nutritional content, no practical use for the individual person standing in the cold, and yet is unmistakably worth seeing. That has been worth seeing for as long as there have been eyes to see it. The aurora will outlast us. Long after every city has been erased, by whatever forces erases cities, the aurora will continue. The solar wind will blow. The magnetic field will turn. The electrons will fall. The oxygen will glow. The sky above the poles will shimmer in green and white and red for an empty landscape of ice or stone, or whatever the world becomes. The aurora is older than us, too. It was there before there were eyes to see it, before there were humans at all, before the mammals, before the great dying events, before the continents were in their current arrangement. As long as the Earth has had a magnetic field and a solar wind to push against it, the aurora has been happening. Billions of years of silent, beautiful, entirely unwitnessed light over an empty, frozen world. We arrived very recently. In geological time, we have been watching the aurora for the thinnest slice of its existence. All the myths, all the science, all the photographs, all the poetry, all the people who stood in the cold and tilted their heads back. It is all very recent, and it will pass, too. The aurora will not notice. It will continue on its own terms, as it always has, for as long as the conditions hold. There is a comfort in that, strange as it might sound. The aurora does not depend on us. It was not made for us. We simply happen to be the kind of creature that can see it and wonder at it. We are very lucky for that. It would be a shame to have eyes and never look. The aurora has a way of putting things in order, not by telling you what matters. It is light, it has no opinions, but by making your usual sense of importance temporarily quiet. The anxieties of the day, the small concerns of an ordinary life, the noise of the world, standing beneath the aurora, these things step back. Not permanently, not because they don't matter, just for a moment, just for as long as you can manage to keep looking up. And then you go back inside. You warm your hands. You sleep, and the aurora goes on. Without you, above the clouds, above the weather, above everything. Shifting and breathing, and very, very old. There is a question that aurora researchers sometimes explore, not in journals, but in quieter conversations, which is whether the aurora has any measurable effect on the people beneath it. Not in the obvious sense of beauty or wonder, but physiologically, chemically. The idea being that geomagnetic activity, which produces the aurora, also produces fluctuations in the Earth's magnetic field at the surface. And the human body, which contains its own electrical systems, heart, brain, nervous system, might in some very small way respond to those fluctuations. The research is preliminary and contested and should be held lightly. But the question itself is quietly compelling, that the aurora, even from hundreds of kilometers above, might touch us in some dim and wordless way, that we might be faintly aware of it, without knowing what we are aware of. The aurora appears in the dreams of people who have seen it. Not metaphorically, literally. People who have had strong aurora experiences report dreaming of the lights for years afterward. The image lodges somewhere deep. It becomes part of the internal landscape, which makes a certain sense. The aurora is unusual enough, vast enough, strange enough in its quality, that the sleeping brain returns to it, tries to process it, tries to understand something. That waking understanding, never quite completed. Dreams and the aurora have in common this quality of elusiveness. Both resist being held. Both dissolve when you try to look at them directly. Both leave behind, when they are over, a feeling that something important happened, even if you cannot say quite what. The connection between the aurora and the quality of the dark around it is worth dwelling on. The aurora appears most beautiful when the surrounding sky is most completely dark. In a city, light pollution washes out the sky, and the aurora, if visible at all, appears as a dim and unimpressive glow. Drive 2 hours from the city. Find a field or a hilltop. Let your eyes adjust to genuine darkness. And suddenly, the same aurora that looked disappointing from the suburbs reveals its full character. Structured, alive, layered. The dark was always there. You just had to go to meet it. This is a way in which the aurora rewards the extra effort. Not the effort of equipment or expertise, though those help, but the effort of going further out, going darker, going quieter. Every additional kilometer from artificial light adds something to the sky above. The Milky Way returns. The faint structures within the aurora become distinguishable. The purple at the lower edge becomes visible to the naked eye, rather than remaining a photographic secret. The darkness is not the absence of something. The darkness is the condition. in which the aurora fully exists. There are dark sky preserves, established specifically to protect areas from light pollution, including areas beneath the auroral oval. The International Dark Sky Association certifies locations that meet standards for darkness. In northern latitudes, some of these certified dark sky parks also happen to be excellent aurora watching sites. The recognition that darkness has value, not just for astronomy, but for human experience and ecology, is slowly growing. More communities near the auroral zone are considering light ordinances that protect the night sky, the way other ordinances protect forests or coastlines. The ecology of the aurora zone is shaped in part by the seasons that the aurora marks. The animals of the Arctic have evolved to live through polar night and polar day. Reindeer, whose migrations take them across vast distances, move in winter across landscapes, illuminated more by aurora and moonlight than by the absent sun. There is some speculation among biologists that reindeer, which have eyes adapted to detect ultraviolet light that humans cannot see, may perceive the aurora differently from us. Whether they see more or less, whether the lights register to them as anything meaningful, we cannot know. But they live beneath the aurora, from birth to death, and seem entirely untroubled by it. The migratory birds of the Arctic navigate partly by the magnetic field, that same field whose beauty is made visible by the aurora. They carry magnetic sensing cells in their inner ear or beak, precise enough to feel the field's direction and intensity. During geomagnetic storms, when the aurora is most intense, this navigation is disrupted. Birds sometimes appear disoriented. The invisible map they rely on becomes unreliable. They fly the wrong way. They land in unexpected places. The aurora, beautiful to us, may be a source of brief confusion to the creatures that navigate by the same forces that produced it. There is something humbling about that. The same event that makes people drive hours and stand in cold fields is an interruption to the flight path of a small bird trying to get home. Beauty from one perspective, disruption from another. Neither more true than the other. The aurora's presence can be felt in cultural exports from the countries that live beneath it. Scandinavian design, its preference for cool blues and whites and greys, its comfort with spare space and long horizontal lines, has been connected by some writers to the visual character of the northern winter. The aurora is part of that winter. Its colors inform the palette, the quality of light it gives. Diffuse, cool, without hard shadows, appears in the design sensibilities of those northern cultures. How much is direct influence, and how much is the shared environment, shaping both the art and the aurora simultaneously? It is impossible to say precisely. But the connection feels real. To anyone who knows both the design and the lights. Music from the far north carries something of the aurora in it too. Joik, the traditional vocal music of the Sami people, the indigenous people of Lapland, has a quality of open space and improvised unfolding that some have compared to the aurora itself. It does not have fixed verses and choruses. In the conventional sense, it circles around a subject, a person, an animal, a place, the way the aurora circles around a pole. Returning, shifting, approaching from a different angle. Never quite the same twice. Contemporary composers working in the far north often speak of the aurora as a kind of collaborator. The composer Olafur Arnalds, from Iceland, creates music that many listeners describe as sounding like the Northern Lights look. He does not program it to be so. It arises from living in the same place, under the same sky, with the same quality of cold light and long, dark winters. The environment shapes the music, the way it shapes everything else in that landscape. The aurora has been described by some neuroscientists as one of the stimuli most effective at producing the awe response in humans. The particular emotion produced by encountering something vast and difficult to fit within existing mental frameworks has been studied as a distinct and important human experience. It is associated with decreased activity in the default mode network of the brain, the region associated with self-referential thinking, with rumination, with the ongoing internal narrative of the self. Awe quiets that narrative. It reduces the self, temporarily, and expands the sense of connectedness to something larger, which is, among other things, a remarkably good description of what watching the aurora feels like. The Northern Lights also have a relationship with the northern spring. In the very early spring, when the polar night has ended and daylight is returning, but the nights are still long and dark enough to show the aurora. This transitional period produces some of the most beautiful displays. The sky is not yet fully dark at midnight. There is a deep blue twilight on the horizon, and the aurora hangs above it. In green and sometimes violet, the contrast between the blue of lingering dusk and the green of the lights, producing a color combination that no artist could easily invent. The world waking up, while the lights still have the sky. A late-season aurora, seen in March or April from Lapland or Iceland, has a particular quality of gift. The aurora season is ending. The days are getting long. Soon the midnight sun will return, and the lights will be invisible for another half a year. Watching an April aurora, knowing it may be among the last for months, gives it a slightly different weight. Not sadness, exactly. Something closer to appreciation. The awareness that a thing is temporary sharpens attention to it. The aurora began to be seriously studied by multiple nations at the same time. During the first International Polar Year, which ran from 1882 to 1883, 12 nations sent expeditions to the Arctic and Antarctic to take simultaneous measurements of magnetic fields, aurora, weather, and other phenomena. It was one of the first great examples of coordinated international scientific effort. Nations that in other contexts might be rivals, sharing instruments and data to understand something no single nation could study alone. The aurora, in that sense, has always promoted cooperation. It is too large to be owned, too globally produced to belong to one country. The solar wind does not respect national borders. The magnetosphere wraps around the entire planet. Studying the aurora has required, from the very beginning, people from different places, agreeing to look at the same sky together. Subsequent international polar years, in 1932 and 1957, deepened this cooperation. The International Geophysical Year of 1957 and 1958 was particularly significant. It coincided with the dawn of the space age, with the launch of Sputnik, and with the first direct measurements of the solar wind and magnetosphere. The aurora theory of Birkeland, dismissed half a century earlier, was finally vindicated by instruments, seeing directly what he had only inferred from the ground. The aurora community today is a global one. Researchers from Norway, Iceland, Finland, Canada, the United States, Japan, China, Russia, and many other countries share data through international networks. Space weather alerts are issued by agencies that monitor solar activity on behalf of the whole planet. The sky above the poles is watched by everyone, owned by no one. The most recent period of intense aurora study has been enabled by machine learning and artificial intelligence applied to aurora science. Convolutional neural networks trained on millions of aurora images can now classify aurora types automatically, identifying arcs, bands, corona, diffuse aurora, steve, and other structures, faster and more consistently than human eyes. These automated systems, running continuously on live camera feeds, can detect a substorm onset within seconds of it beginning, alerting researchers and aurora watchers simultaneously. The science is becoming faster, more precise, more automated. And the aurora continues, indifferent to all of it, in the old way. The very word sublime, in its philosophical sense, as developed by Edmund Burke and Immanuel Kant, describes something that is both overwhelming and elevating at once. Something that is almost too large for the mind, but that the mind strains toward anyway. The aurora is a natural embodiment of the sublime. It is not merely beautiful. Beautiful implies something that fits comfortably within experience. The aurora does not quite fit. It exceeds the usual categories. It requires you to expand slightly, to accommodate it. And in that expansion, something else enters. A kind of spaciousness, a temporary relief from the sense of being enclosed inside your own thoughts. The aurora's light is produced at the quantum level and visible across hundreds of kilometers. Each atom that emits a photon of green light does so according to the precise rules of quantum mechanics. The energy gap of an oxygen electron dropping from one state to another, releasing a particle of light with a very specific wavelength of 557.7 nanometers. That is the green of the aurora. Not approximately green, not sort of green, a precise, specific, exact green, determined by the laws of physics, with perfect consistency across every atom of oxygen in every aurora that has ever existed. Every aurora display you have ever seen in a photograph, or might one day see in person, has that exact green. The same green above Alaska, as above Iceland, as above Antarctica, as above Jupiter's moon, Ganymede, where oxygen aurora has also been detected. One green, everywhere the conditions exist. Physics writing the same number, in light, wherever the problem is posed. There are people who have waited their entire lives to see the aurora and never have, who have traveled to Lapland or northern Canada and been caught under cloud cover every single night, who have stood in the cold waiting and seen nothing. And there are people who have seen it without even meaning to, who stepped outside on a clear evening in Scotland during an unexpectedly strong geomagnetic storm and found the northern sky rippling green, who had no idea what they were looking at and had to have someone tell them. The aurora is egalitarian in this way. You cannot reliably buy it or plan for it with certainty. It arrives on its own schedule and makes its own decisions about who gets to see it. But perhaps that is part of what makes it matter. If you could book it the way you book a cinema ticket, it would be different. It would be a service, not a gift. The uncertainty, the knowing that tonight might be nothing and tomorrow might be extraordinary, keeps it alive in a particular way. It asks something from you. Not money, not planning, just the willingness to go outside and look without guarantees. So let it carry you now, the way sleep carries you. Not with urgency, not with direction, but with a gentle and irresistible pull towards something darker and quieter. The aurora does not try to keep you awake. It has no interest in your attention. It will be there whether you watch or not. And that, in its quiet way, is the most restful thing about it. So let it carry you now, and carry you gently. The lights above the world do not need to know you are watching. They do not need an audience. They glow because the physics says to glow. They move because the magnetosphere is breathing. They fade because the solar wind ebbs. And through all of that ancient and indifferent process, they happen to be beautiful. Not for us. Simply beautiful. The way a snowflake is beautiful. Even in a place no eye will ever see it fall. So let it carry you now. Let the image of it settle over you, like the cold, clear air of a northern night. Imagine the dark sky above your house. Imagine it spreading outward, upward, past the clouds, through the upper atmosphere, into the thin, cold region where the particles fall. Imagine the green light, very far above you, in a place where you are not but could be. Moving, quiet, vast. You are somewhere warm. You are under something soft. Your breathing has already slowed. The day has gone from you, the way the aurora eventually goes. Gradually, without a sharp ending, just a slow return to darkness. Let your eyes close, or let them stay as they are. It doesn't matter. Either way, something is moving above the world tonight. Something green and ancient and unhurried is doing what it does in the long dark above the poles. And you don't have to see it to feel, in some small, quiet way, that it is there. The earth breathes. The sun breathes. The space between them hums with something neither warm nor cold, something that falls along invisible lines and glows, briefly, against the dark. Rest now. The lights are still there. And you are here. And that is enough. That is more than enough.